Imagine living without electricity. No refrigerator, no washing machine, no internet. Sounds like a nightmare, right? But our ancestors in the Middle Ages had solutions that were sometimes smarter than what we use today. They built cooling systems that worked without energy. They developed heating systems that were more efficient than modern furnaces. And best of all, these technologies ran for centuries without maintenance. After the fall of Rome, many ingenious inventions were lost, but in the Middle Ages, new techniques emerged that were perfectly adapted to local conditions. Today, I'm going to show you 12 of these forgotten technologies. Each one could revolutionize your life as a self-sufficient person. Water has always been life, but how do you get it where you need it without electric pumps? The answer lies in water power itself. The water wheel was the engine of the Middle Ages. Imagine a stream flowing peacefully through a village. At its side, a wooden wheel, 3 meters high and made entirely of oak, turns slowly. This wheel not only drives the mill, but also saws, hammers, and even textile machines. A single stream could supply an entire village with energy. The technology behind it is ingeniously simple. Flowing water hits the blades of the wheel and sets it in motion. This rotational movement is transmitted to various tools via gears and shafts. Overshot water wheels, where the water comes from above, achieved efficiencies of over 70%. That's better than some modern turbines. But water wheels could do even more. In the Netherlands, they pumped water out of flooded areas. In mountainous regions, they lifted groundwater to higher elevations, all without a drop of gasoline or a kilowatt-hour of electricity. Then there were the water lifting machines. The Noria, a vertical water wheel with pots or buckets, continuously drew water from rivers and wells. This technology originated in the Orient but was also used in Europe. The principle, the wheel turns with the flow, the containers fill with water at the bottom and empty into channels or basins at the top. Even cleverer were the pumping stations with Archimedes' screw. A spiral screw in an inclined pipe transports water upwards when it is turned. Windmills drove these screws and thus drained entire areas of land. Without this technology, Holland would still be a swamp today. Medieval water pipes were also impressive. While the Romans relied on stone and lead, medieval engineers experimented with wood and fired clay. Hollowed-out tree trunks, mostly oak or elm, served as pipes. These were reinforced with iron rings and sealed with pitch or resin. Such wooden pipes lasted for decades and were much cheaper than metal pipes. Clay pipes were even more durable. They were fired in special kilns at high temperatures until they became rock hard. These pipes withstood frost and root pressure better than many modern plastic pipes. In German cities such as Augsburg and Nuremberg, such pipe systems supplied thousands of people with fresh drinking water. Why were these systems more reliable than modern pumps? Quite simply, they had no moving parts that could break. A water wheel runs as long as water flows. No electronics to fail, no filters to clog, no motors to overheat. Today, micro hydropower is experiencing a renaissance. Small water wheels with a diameter of only 1 meter can generate enough electricity for a homestead. All you need is a stream with a constant flow and some manual skills. The technology is the same as it was 800 years ago, only the materials have become more modern. A homemade water wheel costs a fraction of a solar system and runs 24 hours a day. No batteries, no inverters, just pure mechanical energy. For self-sufficient people living near streams or small rivers, this is the perfect solution. While water wheels powered villages, other technologies provided cozy warmth during the cold months. The tiled stove was the king of medieval heating technology. Imagine a stove that not only heats but also stores heat for hours and releases it evenly. Tiled stoves consisted of special clay tiles that were inserted into a latticework of clay and stones. The secret lay in the mass. These stoves often weighed over a ton and stored heat like a giant battery. Once properly heated, they radiated heat for 12 to 24 hours. You only had to add wood twice a day, and the whole room stayed cozy and warm. The tiles were fired at over 1,000 degrees and glazed, which not only looked beautiful, but also optimized heat emission. Even more impressive were the hypocaust heating systems, a legacy from Roman times that was further developed in the Middle Ages. This underfloor heating system worked without pumps or pipes. The trick: hot air circulated under the floor through a system of brick channels. A central furnace, usually in the kitchen or basement, produced hot gases. These flowed through cavities under the floor and rose through channels in the walls. The heat was distributed evenly throughout the room without having to carry wood into each individual room. Monasteries and castles used this technique to heat large halls. But what about cooling? This is where medieval builders showed true ingenuity. The ice cellar was more than just a hole in the ground. These underground chambers were strategically located, usually on north-facing slopes or under thick stone walls. In winter, ice was cut and stored in layers with straw or sawdust. The construction method was crucial. Thick stone walls, often 1 meter thick, insulated against heat from outside. Double doors with airlocks prevented warm air from entering. A drainage system drained meltwater without damaging the insulation. This kept the ice frozen until autumn. Earth cooling chambers work on a similar principle. At a depth of 2 meters, temperatures remain constant between 8 and 12 degrees Celsius all year round, perfect for storing meat, dairy products, and vegetables. These natural refrigerators required no energy and kept food fresh for weeks. Smoke kitchens cleverly combined heating with cooking. The smoke from the fireplace was not vented directly outside, but was directed through a system of channels and chambers. In the process, it transferred its heat to the surrounding rooms. At the same time, the smoke smoked meat and fish that were hung in special chambers. These systems were so efficient that they used a fraction of the fuel consumed by modern heating systems. A tiled stove achieved efficiency levels of over 80%, while open fireplaces only managed 20%. Today, these techniques are experiencing a renaissance. Modern tiled stoves combine traditional construction with optimized combustion. Earth cooling chambers are being rediscovered as a natural alternative to refrigerators. They are the perfect solution for energy self-sufficient houses. No electricity bills, no maintenance-prone technology, just clever physics and proven craftsmanship. When you buy bread today, you don't think about how the grain was ground. But imagine if you had to crush every grain by hand. Medieval millers had a better solution: the windmill. These tower-like giants shape the European landscape. A typical windmill was 20 meters high, and its wings had a span of 25 meters. The ingenious thing about it was that it used a source of energy that was always available and cost nothing. The technology was sophisticated. 4 large canvas sails caught the wind and transferred the power via a system of wooden gears to 2 massive millstones. The upper stone, the runner, rotated above the stationary bottom stone. Grain was poured between these stones and ground into fine flour. But windmills could do even more. They pumped water from flooded areas, pressed oil from seeds, and even sawed wood. Thousands of these mills stood in Holland, making the land habitable in the first place. Without them, much of the Netherlands would still be sea today. The key lay in adaptability. Millers could adjust the sails depending on the wind strength. In storms, the sails were reefed, and in light winds, they were fully extended. The entire mill cap could be rotated to give the sails optimal wind. This fine-tuning required years of experience. Even more impressive were the mechanical power amplifiers for oil presses and wine presses. The screw press multiplied human power 100-fold. A simple lever, combined with a threaded spindle, generated enormous pressure. Imagine you want to press walnuts. By hand, you can probably exert 10 kilograms of pressure. With a screw press, you can exert a ton. The crushed nuts were filled into coarse linen sacks and placed under the press. The spindle was slowly turned until the golden oil ran out. Wine pressing worked on the same principle. Grapes were poured into a wooden trough and covered with a heavy board. The screw press pushed the board down and squeezed every drop of juice from the grapes. This juice was purer and clearer than that produced by the traditional method of treading. Meat preservation was essential for survival, especially in winter. Smokehouses combined heat, smoke, and time to create the perfect preservation method. These brick chambers had a fireplace in the basement and several floors with hooks for hanging meat. The secret lay in the choice of wood. Beech, oak, and fruit tree woods not only gave the meat flavor, but also antimicrobial substances. The smoke slowly dried the meat and formed a protective layer against bacteria. Meat preserved in this way was edible for months. Curing techniques complemented smoking. Meat was pickled in brine or rubbed with salt mixtures. The salt drew water out of the meat and made it inedible for harmful microorganisms. Combined with spices such as juniper or caraway, this created delicacies that are still appreciated today. Fermentation was the supreme discipline of preservation. Sauerkraut, pickled cucumbers, and fermented dairy products were created through controlled fermentation. Lactic acid bacteria converted sugar into acid and preserved food naturally. These techniques work just as well today as they did back then. Small windmills can grind grain for a family. Smokehouses can be built in the garden. Fermentation only requires jars and time. For self-sufficient people, these are the basics of self-sufficient food production. Now that we've seen how windmills processed grain, let's take a look at how medieval craftsmen made their tools. Without machines, without electricity, but with a precision that puts modern manufacturing to shame. The potter's wheel was a marvel of mechanics. Imagine a heavy stone disc mounted on a vertical axis. A powerful kick with the foot sets it in motion, and the stored momentum keeps it rotating evenly for minutes. This kinetic energy allowed the potter to have both hands free and to shape perfectly symmetrical vessels. The secret lay in the weight and the bearings. The flywheel often weighed over 100 kilograms and was made of dense stone. The axle ran in wooden or stone bearings that were lubricated with animal fat. Once set in motion, the system rotated so evenly that potters could form wafer-thin vessels. Firing kilns reached temperatures of over 1,000 degrees without any gas or electricity. These dome-shaped structures made of fireproof bricks made perfect use of the chimney effect. Wood was burned in a separate combustion chamber. The hot gases flowed around the pottery and rose through a chimney. The construction was crucial. Thick walls stored the heat and released it evenly. Several flues optimally directed the flames around the fired goods. Experienced potters could tell the exact temperature from the color of the flames and knew exactly when their ceramics were finished firing. Blacksmith bellows generated the extreme temperatures required for metalworking. These leather-covered constructions functioned like giant lungs. Two chambers worked alternately. While one filled with air, the other pushed air into the forge. The key feature was the valve system. Simple leather flaps prevented the air from flowing back. A steady stream of air heated the charcoal to over 1,500 degrees. At this temperature, iron became as soft as butter and could be shaped perfectly. Two journeymen operated the bellows alternately, keeping the fire constantly hot. Looms transformed raw fibers into complex fabrics. These wooden frames stretched the warp threads taut, while the weaver passed the weft thread through with a shuttle. Different shafts alternately lifted different warp threads, creating intricate patterns. The spinning wheel was the precursor to weaving. It twisted fibers into even threads at a speed 10 times faster than hand spinning. A flywheel stored energy, while a clever gear ratio turned the spindle at high speed. Sawmills combined water power with precise woodworking. A water wheel drove a crankshaft via gears, which moved a heavy saw blade up and down. The log was slowly pushed against the blade and cut into even boards. This mechanical precision was impossible to achieve with hand saws. Why were these tools easier to maintain than modern machines? The answer lies in their simplicity. No electronics to corrode, no motors with hundreds of moving parts. Just sturdy mechanics made of wood, stone, and iron. A well-built loom worked for centuries. Potter's wheels were passed down from generation to generation. These tools were built to last. Imagine you are on the high seas, hundreds of kilometers from the coast. No GPS, no compass, just you and the stars. Medieval sailors mastered this challenge with instruments that would still work today. The astrolabe was the Swiss Army knife of navigation. This circular disc made of bronze or brass could do everything: determine latitude, tell the time, calculate prayer times, and even make astrological predictions. The genius of it was its precision. Experienced navigators achieved an accuracy of a few kilometers just by observing the stars. It was elegantly simple to use. You held the astrolabe vertically and aimed it at a known star. The position of the movable pointer on the engraved scale told you your geographical latitude. Combined with star charts, sailors always knew where they were. This technique worked day and night, in all weathers, as long as the sky was visible. Arab scholars perfected the astrolabe in the 9th century. It reached Europe via Spain and revolutionized seafaring. Christopher Columbus navigated to America with an astrolabe. Vasco da Gama circumnavigated Africa with it. These palm-sized instruments made the discovery of new worlds possible. Sundials were the atomic clocks of the Middle Ages. No batteries that run out, no mechanics that break down, just a shadow that moves with mathematical precision. Medieval clockmakers engraved complex scales in stone and bronze that showed not only the hour, but also the seasons and even the phases of the moon. Their manufacture required astronomical knowledge. Each sundial had to be calculated for its specific location. The angle of the shadow stick depended on the latitude. The division of hours varied according to the season. Masterful sundials showed the time to within 5 minutes, and in perfect conditions even more precisely. Portable sundials fit in your pocket. Foldable models made of ivory or wood were status symbols for wealthy merchants. They worked anywhere in the world as long as you knew the geographical latitude and the sun was shining. The magnetic compass came to Europe from China in the 12th century and changed everything. A magnetized needle floating on a cork always pointed north. This simple invention made navigation possible even when the sky was cloudy. Medieval compass makers developed sophisticated cases. The needle floated in a bowl filled with oil, which protected it from vibrations. A wind rose with 32 directions enabled precise course determination. Experienced captains even compensated for magnetic declination, the difference between the magnetic and geographic North Pole. Star charts were the road maps of the Middle Ages. These celestial maps, drawn on parchment, showed the position of stars at different times of the year. Navigators memorized the movement of the stars and were thus able to determine their position even without instruments. The quadrant was a simplified astrolabe, a quarter circle with degree markings and a plumb line attached to it. This allowed sailors to measure the height of stars above the horizon and calculate their position. Easier to build and use than an astrolabe, but almost as accurate. Today, these navigation techniques are experiencing a renaissance. Sailors are relearning astronomical navigation as a backup for GPS. Scouts orient themselves with a compass and map. Survival experts build sundials out of sticks and stones. Why is this relevant? Because technology can fail. Satellites can be shut down, batteries can run out, electronic devices can break. But the stars always shine. The magnetic compass works without electricity. These medieval techniques are your life insurance when modern navigation fails. These 12 technologies have one thing in common. They have been working reliably for centuries, without electricity, without complicated maintenance, without expensive spare parts. While our smartphones are obsolete after 3 years, medieval water wheels are still turning. This is more than just nostalgia. It is practical wisdom. Our ancestors built for generations, not for planned obsolescence. They used local materials and natural energy sources. They developed systems that repaired themselves or were so simple that anyone could understand them. For them, sustainability was not a marketing term, but a necessity for survival. Resources were precious, waste was deadly. That's why they created technologies that worked in harmony with nature rather than against it. Which of these techniques would you like to try? Maybe a small water wheel for your stream? A smokehouse for the garden? Or perhaps a sundial for the terrace? Write your ideas in the comments.